Hello AP Statistics students. This is part 2 of our video here. I ended the other video with just independence. And so this will give us another chunk here about our probability rules. So we've got a couple already. The first one we learned was the general addition rule, all right, for unions, all right, the probability of A or B. So we got that one already. Put it here again for us. We did our conditional probability rule last time, but now it's time to do one for and, the intersection of two events. How do we find a general rule to get the intersection of two events? So I got a simple scenario here to help us walk through to get to that general formula. All right, so simple scenario here. Suppose 55% of high school students participate in a sport. Roughly 6% of these athletes go on to play a sport in college. What percent of high school students do both? Play a high school sport and play in college. All right, so we're going to use that idea to build this intersection rule for and statements. All right, and to do this one, hopefully it's a bit intuitive here. If 6% of the 55% go on to play a college sport, how many do both? Well, 6% of, remember what of means in mathematics? It means multiply. So we're going to take 55%, oops, that won't have the percent sign, will it? And multiply by 6%. That is 6% of the 55%. So we type that in and we get 3%, 0.033 actually. So 3.3% of high school students play a high school sport and go on to play in college. And so we're going to use this idea. That gives us our and statement. We're going to build our formula off of this example right here. So what did the 55% represent? 55% of high school students participate in a sport. Well, that is a probability. The probability that a high school student plays a high school sport, I guess I'll go HSS for high school sport, is 55%. Now, the 6% is a bit more tricky. Roughly 6% of these. All right, what does the pronoun these point towards? 6% of the 55%. All right, well, that is the probability that somebody plays a college sport. I'll put CS, but we know something about them. I'm only looking at these. I have a condition. What these am I looking at? The 55% that played a high school sport. All right, I'm only looking at those high school sport athletes, and so that is my given. That is my condition. That equals 0.06. And then we multiplied them together. Why? Because we were finding the ones that did both, a high school sport and played in college. So the probability that somebody played a high school sport and a college sport is equal to the 55%, but that I'm going to write it as a probability, the probability of playing a high school sport times the 6%, but that was the probability of playing a college sport given they also played in high school. So there is my general multiplication rule for and as a specific example. Now let's generalize that, get rid of the high school and the college and just A's and B's. The probability of A and B is equal to, all right, well, the probability of HSS is just the A, so the probability of A times the probability of, well, the next one, came from the B slot, probability of B given HSS is our A. So there is the general multiplication rule for an intersection probability right there. Put a box around that one. Now, one interesting thing to look at, this is actually just a reordering of our conditional probability formula. So if you remember from last time, our conditional probability, the probability of A given B is equal to the probability of A and B divided by the probability of B. Well, if I want to get the AND statement by itself, all I have to do is multiply the denominator to the other side. So the probability of A and B is equal to the probability of A given B times the probability of B. Now, as you can see, the order of the letters changed just a little bit, didn't it? But hopefully you realize that the order of the AND, the order of the intersection, doesn't actually matter. All right, again, go back to a Venn diagram. If I want to find the intersection here, does it really matter which one is A and which one is B? I'm still finding the ones that do both A and B. The order doesn't actually matter in this case. All right, but it is very, very similar to the conditional probability formula. Just a reordering with some algebraic manipulations. All right, let's use this now. So the Pew Internet and American Life Project reported that 79% of teenagers from 13 to 17 use social media, and that 39% of teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. Find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments or likes. All right, let's write out what all these are in probabilities here. So what does the 79% mean? All right, 79% of teenagers use social media. So what is the probability that a teenager uses social media? Is equal to 79%. What does the 39% means? That's those who feel pressure, but it's only of those who use social media. That is a condition. That's our conditional statement. So that's the probability of those who feel pressure given they use social media. Is equal to 39%. So they are asking us for what is the probability that a randomly selected teen uses social media, so social media, and feels pressure to get lots of comments. All right, so we're going to use our AND formula. That is going to equal the probability of social media, times the probability of pressure given social media. The probability of pressure given, I'm going to abbreviate there, given social media. So we just plug in our numbers there. That will be 73% or 79% times 39%. I guess I don't need the percent there, do I? And that will give us our answer for both. There we go. Equals 0.79 times 0.39 is about 31%. So there's a 31% chance that a randomly selected teenager will be using social media and feel pressure to post something that gets a lot of likes. All right, now, one tool that can help us do all of these is called a tree diagram. All right? A tree diagram helps organize all this information and make it much easier to do these rules. So, here's our scenario. Shannon hits the snooze button on her phone alarm 60% of the time on all school days. Whew. Only 60%? I do it every day. If she hits the snooze, there is a 70% chance that she makes it to class on time. Yeah, that sounds about right. It's dangerous to hit that snooze button. If she doesn't hit the snooze and instead gets up, there is a 90% chance she gets to class on time. Yeah, there's always a chance you don't get there. This can easily be modeled by a tree diagram. All right, so here's the tree diagram. First, we start here. So first, there is a 60-40 chance for what Shannon does first. There's a 60% chance she hits the snooze button. And that means that must be a 40% chance, the complement, that she doesn't hit the snooze button. All right, now, once she hits the snooze button, there's only a 70% chance she'll be on time, which means, the complement, a 30% chance she will be late. And then the same thing on the other one. If she doesn't hit the snooze button, all right, she gets up on time, there's a 90% chance she'll be on time. But if there's a 90% chance she'll be on time, there is a 10% chance she will be late. The complement again. So it's just sort of a flow map of all the probabilities and the events as they take place. But this organizes a lot of what we need to do, because now a question like this, right here, what is the probability that tomorrow, a random day, let's say, tomorrow Shannon hits the snooze and is late? All right, well, what we can do is follow that on our tree diagram. All right, that she hits the snooze, so we're going this way, so 60% chance that that'll happen, and is late. That's this way, right? To get to and is late. Well, to find that probability, all we got to do is multiply along that line. 0.6 times 0.3. That will give us the probability of the and, because this 60% right here is the probability of a snooze. But this 70 and this 30%, well, that's a condition now. That's a conditional probability, because we know, as they have it right here, that Shannon has hit the snooze button. So this 70% is the probability that she is on time, given that she's already hit the snooze. And this one down here is the probability that she will be late, given that she's hit the snooze. So this second round of probabilities here, these are all conditionals. And the condition is right here. Well, that fits our and formula just perfectly. All right, so 0.6 times 0.3 is 0.18. So on any random day, there is an 18% chance that Shannon will hit the snooze and be late. All right, there's no condition there. We're not saying that she will hit the snooze, but there's an 18% chance that she will hit the snooze and be late. All right, what is the probability that tomorrow Shannon won't hit the snooze button, but will still be late? That's a possibility that could happen to all of us, right? So on any given day, what's the probability that that will happen? Well, all we got to do is slide along our tree diagram. All right, that she won't hit the snooze, that's 40%. And she will still be late. That's another 10%. All right, so that is the path we are going. So that will be 40% times 10% is equal to, that'll be 4, won't it? 0.4 times 0.10 is 0.04. There is, on any given day, there is a 4% chance that Shannon will not hit the snooze button and still be late. All right, now a trick question. What is the probability that Shannon will be late tomorrow if she hits the snooze button? Pause the video, think that one out maybe, all right? It's a trick question. I'm giving you that hint right now. Try it out. All right, did you figure it out? Why it was a trick question? This one is not like the others. Did you see the difference in wording? All right, there's no and statement. This is a conditional statement. What is the probability that Shannon will be late? The probability of late. If she hits the snooze button, well, that means I know she's hitting the snooze button. That is not an intersection. That is the probability of being late given she hits the snooze. And isn't that this one right here? All right, given we hit the snooze button, there is still a 30% chance. Just remember that now that we have this tree diagram, you don't always just multiply along the lines. Okay, that only works for an intersection. Okay, if you're somehow doing an and statement, that's when you multiply. All right, but let's take it up a notch. What is the probability that Shannon will be late on a random day? Ooh, well now I don't care how she's late. I don't care if she hits the snooze button or doesn't hit the snooze button. I just want to know what is the probability that Shannon will be late, no matter what way that happened. Well, we have to figure out the different ways that it could happen. All right, what are the different ways that she could be late? Well, let's see, draw. One way she could be late is if she hits the snooze button and is still late. The other way that she could be late is if she doesn't hit the snooze button and still becomes late. So there's two ways this could happen. Those are what we call mutually exclusive events because they cannot both happen. All right, she either is going to be late by hitting the snooze button or she's going to be late by not hitting the snooze button. There's no way you can do both of those at once. That is mutually exclusive. We did that in a video a little while ago, didn't we? So what we're going to do is we're going to add those two possibilities. One of them is 0.60 times 0.30. That's the first one, plus the probability of the other one, which is 0.40 times 0.10. Those are the two ways that she can be late. They're mutually exclusive, so we can add them together. All right, if I want to write out the probabilities, that is the probability of being late given, the first one is hitting the snooze, plus the probability of being late given no snooze. Add those two together. let's see, that one was 0.18 plus, we did that one as well, 0.04. So there is a 0.22 or a 22% chance that she will be late. All right, in any method, either hitting the snooze or not hitting the snooze, overall there's a 22% chance she will be late. All right, a couple more here to really use this tree diagram. Suppose Shannon was late to class today. What is the probability that she hit the snooze button? Whoa, this is like going backwards, isn't it? So we now know she's late. What is the probability that she hit the snooze button? All right, here is where we want to start using our formulas. All right, so I want to know the probability of the snooze given that we are late. Okay, so I'm going to use the probability rule here for conditions. That is the probability of snooze and late divided by the probability of being late. So what does that equal? Well, we've done both of these, haven't we? The probability of hitting the snooze and being late is hitting the snooze and being late. That is the 18, isn't it? So the top will be 18% divided by, what's the probability of being late? Well, to find that, that's where we had to add the two possibilities, isn't it? So that took another step, but thankfully we've already done that step. That was 22%. So 0.18 times 0.22, divided by 0.22 is equal to 82%. Hopefully that makes a little bit of sense. If you are late, why was it that you were late? Probably because you hit the snooze button. So there's an 82% chance that she hit the snooze button if she was late. So when she stumbles into class late, everyone knows there's an 82% chance it was because she hit the snooze button. All right. I think I got another one of those. Suppose Shannon was on time to class today. What is the probability that she hit the snooze button? Ooh, all right, that's the same idea, but backwards. So she was on time, so that is my given. On time. Now, what is the probability that she hit the snooze? So that is the one that goes right here. I would challenge you here to write that out as a probability on your own. Use the formula and then see if you can figure out what that is before I do. All right, let's do this. So that will be first the intersection on top, probability of snooze, and on time, divided by the probability of being on time. Let's see, I do believe we have some of those. The probability of a snooze and on time. The probability of a snooze and on time is right here, isn't it? I don't think we've done that one yet. So 0.6 times 0.7. So remember, an and statement, you can multiply along that tree diagram. So that is 42%. 0.42 divided by, what is the probability of being on time? All right. I'll do this both ways here. One, if I know it's a 22% chance of being late, well, the complement of that would be 78%. So I know this answer has to be 78, but let's pretend for a second I don't know it's 78, okay? So I now need to do the probability of being on time. Well, there's two ways to be on time. This one. The other way we could have been on time was this one. Remember, we add those together. So it'll be 0.6 times 0.7 plus the other way, which was 0.4 times 0.9. Yeah. So those are the two different ways we can be on time. That will give us the probability of being on time. So 0.6 times 0.7 plus 0.4 times 0.9. I really hope it is 78. Yes. So 0.42 over 0.78 is 54%. So what the heck does that number mean again? She was on time. What is the probability that she hit the snooze button? So even if she's on time, there's still a 54% chance that she hit the snooze. All right, one more problem here I'd like you to try to do here. Read that one, pause the video, try it out. I will have the answers pop up here in just a second, but I want you to try that first. All righty, you ready for the answer? Hopefully you did actually pause it to try this out. Interesting medical application here. So here is the tree diagram that you have to do for this. So they first tell us there's a 1% chance of having cancer. All right, well that means there is a 99% chance that you don't. So you had to figure that one out. All right, then the other statistic they give us here is the 3%. For those women who have cancer, the probability of a negative mammogram is 3%. So they give us this one, and that means we have to find the complement. 97% will test positive if 3% test negative. All right, so that's how we fill this out. You have to add up the complements yourself. So 6% who don't have breast cancer get a positive result. So that means 94% who do not have cancer get a negative result. So they asked for the probability that somebody is testing positive. So we know they tested positive for breast cancer. That's our given. Find the probability that she actually has breast cancer. All right, so that's the probability of cancer given a positive test right here. They told us she had a positive test. Now what's the actual probability she has cancer? Well, first I use the rule for a conditional probability. That's right here. That's just our general rule. And then I had to plug in the numbers. So the probability that you have cancer and a positive test, that's this path right here. All right, so 0.97 times 0.01 divided by the probability that you have a positive test. So what are all the ways you can have a positive test? Well, that's one of them. What's the other way you can have a positive test? If you don't have cancer, but still get a positive test. That is still a possibility. Those are the two paths to have a positive test. You add them together because they are mutually exclusive. So you got all your numbers, plug it in, and you get 14%. So there is a 14% chance of actually having cancer after a positive mammogram test. That's kind of weird, isn't it? There's only a 14% chance after a positive result. All right, so that is how we can use a tree diagram to do our intersection probabilities, the AND probabilities.